Hello and welcome to week 10's problem solving session. So today we'll first solve last year's week 10 assignment, then we'll solve this year's week 10 practice assignment, and then we'll solve this year's week 9 assignment. Okay, let's start. Uh, the first problem is that A be a square matrix with entries from 0, comma 1, which of the following statements is or are true. Select all that are correct. The options are determinant of A equals to 0 implies permanent of A equals to 0. Determinant of A not equals to 0 implies permanent of A not equals to 0. Option C is permanent equals to 0 implies determinant equals to 0. Option D is permanent not equals to 0 implies determinant not equals to 0. And none of the above options. So the answer to this problem is B and C. So first note that if we prove if we prove that any one of the B or C is correct, then the other would be automatically correct because they are contrapositives of one another, right? So let's prove that B is correct. Okay. So uh, we know that the determinant of A is here. Sn is the set of all permutations on n elements. So if determinant of A is not equals to 0, then there exists a sigma such that product I in n ai comma sigma I is not equals to 0. Now, permanent of so this is the permanent of A, and now I'm claiming that this is non-zero, and the reason is the following. So notice that because the matrix is 0, 1, even if one of the terms product I in n ai sigma is not equals to 0, then the permanent is. And the reason for this is that the matrix is 0, 1. So, and there is no negative sign over here. So there are no cancellations. So if one of these terms is non-zero, then the permanent is going to be non-zero. But such a sigma exists because the determinant is non-zero. And hence, yeah, so determinant not, we have proved that determinant not equals 0 implies permanent not equals to 0. And it also implies that permanent equals to 0 implies determinant equals to 0. So now, clearly option E cannot be true. So now let's see why option A and D are false. Now notice that option A and D are counterpositive of one another, so it's enough to show that one of them is false. Okay, so let's show that A is false. So it suffices. So in A, we want to show that so to prove that A is false, all we need to do is construct a 0, 1 matrix such that the determinant is 0, but the permanent is not 0, right? And here's one such matrix like this. And the determinant of A is equal to 0, but the yeah, so we have a matrix which is 0, 1. But the determinant is 0, but the permanent is not. So option A is false, and so option D is also false. So let's look at the next problem. So the next problem is, consider the directed graph G in the figure below. The number of cycle covers in G is dash. So recall that. Okay, so now let's look at this problem. Over here, we are given a directed graph, and we are supposed to find the number of cycle covers in G. Now, recall that a cycle cover is a disjoint union of cycles such that every vertex appears in at least one cycle. Okay, so now let's count the number of cycle covers over here. So, okay, so if we start from X, we have two possibilities. We can take either this edge or this edge. So let's first take the XY edge. So we get X to Y. From Y, we have two possibilities, going back to X or going to Z. So let's go to X. Now, so this is one cycle in the cover. Now, starting from W, we have two possibilities, going to X or going to Z. But we can't go to X because then the cycles won't be disjoint, right? Because X would be in both cycles. So we'll have to take this edge. And once we take this edge and reach Z, there is only one possibility, taking this edge back. We can't take this edge because then again the cycles won't be disjoint. So the another cycle in this cover is W, Z, W. So that's one cycle cover. All the four vertices are covered. Another cycle cover is, so again, starting from X, we take this edge. So it's X to Y. Now, starting from Y, we can take this edge. So Y to Z. Then, now, okay, we can't go back to Y because then we'll be left with W, and W has no self loop. So, yeah, if you were to go back to Y, then W won't be covered. So, we'll have to go to W. And from W, we'll have to go to X because if we can't go back to Z, because then, yeah, this would be, yeah, then like this would be, okay, so if we went to Z, then to get we'll have to go back to Y and to X, and then we'll have these three cycles in our cover, but these three are not disjoint. So this is not a valid cycle cover. So we'll have to go back to X. So these are two cycle covers. Are there more? Yeah. So far we have been only taking this edge, but we could have taken this edge. So if we take this edge, then we go from X to W. Again, we have a choice. Go to Z, or go back to X. Let's first go back to X. Then, just like in the case of this cycle cover, the next cycle we'll have is Y, Z, Y. Yeah, so that's one more cycle covered. Now, starting at X, we took this edge and then took this edge back, right? We could have taken this edge and this edge, and that would give us one more cycle covered. That would be X, W, Z, Y, and X. And these are the only cycle covers because there are only two possible edges out of X, and we have explored all the possibilities starting from those edges, right? So the number of cycle covers is four. Yeah. So is this fine? Okay, so let's move on to the next problem.
But we did 6 times, right? The cycles we went, and then answer is four.
Oh yeah, yeah. Okay, so the cycle cover is a disjoint union of cycles that covers all the vertices. So even though there are two cycles over here, they are just one cover because only together can they cover all vertices, right?
Okay, okay.
Yeah, so it's
Mm.
the number of cycle covers, not the number of cycles. Yeah, because if we just had to
Clear,
find the
clear.
number of cycles, it would have been more because you could have done something like this as well, just this. Yes, let's look at the next problem. The next
Okay.
problem is suppose G is a bipartite graph. Consider a graph G prime, which is defined as the disjoint union of G and H, where H is the graph on four vertices. Depicted in the below figure, if G has K perfect matchings, then which of the following is the number of perfect matchings in G prime? And the options are 0, K, K plus 2, K plus 4, 2K, and 4K. Yeah, so this needs to be worked out. So I won't ask you what the answer is, but if you want to guess, you can. Okay, so yeah, so the answer is 2K, and let's see why. So let M be a perfect matching in G, and any perfect matching G prime will have to be of the form. Okay, then any perfect matching of G prime containing M. Union. So we can take this matching or we can take this matching. Okay, so starting from a matching uh, in G, starting from a matching M of G, we can construct these two matchings of G prime. Now I'm claiming that the only way to get a matching in G prime is by starting off with a matching from G and doing this. And the reason is that there are no edges between vertices in G and vertices in H, right? So since there are any perfect matching in G prime must contain some perfect matching M of G. Yes, but the only way of constructing perfect matchings is taking a perfect matching and taking this or this. Okay, so starting from every perfect matching in G, we can get two perfect matchings in H, right? So the number of perfect matchings in G prime is equal to 2 times the number of perfect matchings in G, which is 2k. Yeah. So number of perfect matchings in G prime is just 2k. Is this fine? Okay, so I hope this is fine. So let's look at the next problem. So in the next problem, uh, we have two Boolean formulas, phi and psi, on the same set of variables x1 to xn. Suppose that phi has k1 satisfying assignments and psi has k2 satisfying assignments. So if phi or psi has k3 satisfying assignments, and what is the number of satisfying assignments of phi and psi? K1 plus k2, k1 k2, k1 plus k2 minus k3, k1 plus k2 times k3, and cannot be determined from the given information. So what would be your guess? Okay, yeah, so the answer is C.
The first,
Yeah,
third one. Okay.
yeah. Okay, so let's see why. So let me claim this. So let S be the set of satisfying of phi, T be the set of satisfying assignments of psi, uh, A be the set of satisfying of phi, okay, phi and psi. Then A is S intersection T. Okay, so let's first prove this claim. So one way to prove the claim is to prove that number one, A is a subset of S intersection T, and number two, A contains S intersection T. Okay, uh, yeah, so let uh, A1 to AN A. So A1 to AN is a satisfying assignment of both of phi and psi. So since A1 to AN, okay, rather let me write it like this. Since phi and psi of A1 to AN is true, phi of A1 to AN is true, and psi of A1 to AN is also true, right? And so A1 to AN is satisfying assignment of both phi and psi. And so A1 to AN is in S intersection T, implying that A is a subset of S intersection T. Okay, so now let's do the other direction. So let A1 to AN be in S intersection T. Then uh, phi of A1 to AN is true, and psi of A1 to AN is also true, right? So phi and psi. This is also so A1 to AN is in A and S intersection T is a subset of A. Okay, so now we have a characterization of the set of satisfying assignments of phi and psi. And now also let's also prove the same characterization or a similar characterization for the set of satisfying assignments for phi or psi. So most of the claim is the same. So let me just copy it. Yeah, so as before, let S be the set of satisfying assignments of phi, T be the set of satisfying assignments of psi, uh, B be the satisfying assignments of phi or psi. Then the claim is that P equals S union T. And yeah, the proof would be along similar lines as the proof of claim one. So let's quickly do it. So let A1 to AN be in then uh, phi or psi is equal to 1. And so at least one of the two phi of A1 AN uh, is true. So A1 to AN is in S union T. Uh, P is a subset of S union T. Similarly, in the other direction, P in S union T, then so if A1 to AN is in S union T, it's in at least one of the S and T, right? So at least one of the two is one. So phi or psi of A1 An is 1 and yeah, so A1 to An is in P and S union T is a subset of, yeah, so both, like B is a subset of S union T, S union T is a subset of P, and so both are the same. So now we have these two claims, and using these two claims, let's try to solve the problem. So in the problem, we have to find the number of satisfying assignments of phi and psi, right? So we are supposed to find the cardinality of A. So cardinality of A is equal to cardinality of S intersection T. And okay, so now we know that cardinality of S union T is the cardinality of S plus cardinality of T minus cardinality of S intersection T. So cardinality of S intersection T is, and from plane 2, this is just minus, and in the question, we have been given all these three cardinalities. So S is the set of satisfying assignments of phi. So size of S is K1. T is the satisfying set of satisfying assignments of psi. So its size is K2. And B is the size of satisfying P is the set of satisfying assignments of phi or psi. So its size is K3. So the answer is K1 plus K2 minus K3. So is this fine? So let's look at the next problem. So in the next problem, we are given Boolean formulas phi and psi with R and S satisfying assignments respectively. And which of the following can we not construct by combining phi and psi with some other variables and logical operators? The options are a Boolean formula with R square plus S cube satisfying assignments, a Boolean formula with R plus S the whole squared plus 2 S square satisfying assignments, a Boolean formula that is R square times S square plus 100 R satisfying assignments, and a Boolean formula that is R cube S minus R S square satisfying assignments. So which of this is true? Or which of this can we not construct?
Last one, I think.
Yeah. Okay, so in the class, you might have seen how to, given two formulas phi and psi, how to construct a formula with whose number of satisfying assignments is the sum of the number of satisfying assignments of phi and psi. So, do you recall this construction, or should I give this construction again?
Can you give it again?
Yeah. Okay. So, so basically, the building blocks of these three are going to be the following two constructions. The construction that lets us add the number of satisfying assignments of two formulas, and the construction that lets us multiply the number of satisfying assignments of two formulas. So, given phi and psi, define the formula. Okay, yeah. Okay, lost network connection. Because I lost connection for a while. Can you see my screen?
Screen is visible.
Okay, yeah.
We couldn't hear you.
Okay, okay. So let phi be a formula on uh, z on in variables z1 to zn, and psi be a formula in z1 to zn. And without loss of generality, we can just assume that n is greater than m. Otherwise, we'll just switch the roles of phi and psi. Okay, so now what we'll do is define the formula phi plus psi on, so we'll define this formula as follows. So it will be a formula in x, okay, let me not write, I'll just write it. So it will be a formula x1. Okay, so we'll define a formula phi times psi as follows. It's just going to be the end of phi and psi, but on different sets of variables. So here x1 to xn and y1 to ym are disjoint sets of variables. Okay, and the claim is that the number of satisfying assignments of phi times psi is going to be the number of satisfying assignments of phi times the number of satisfying assignments of psi. And the reason is the following. So when is the assignment x1 to xn, y1 to ym going to satisfy phi and psi? If and only if it satisfies phi and psi both, right? So x1 to xn must be a satisfying assignment of phi, and y1 to ym must be a satisfying assignment of psi. So to construct a satisfying assignment of phi times psi, we can pick any satisfying assignment of phi and any satisfying assignment of psi and combine them. And yeah, so for every satisfying assignment of phi, we have size of psi many satisfying assignments of phi dot psi. And so, like when we sum over all satisfying assignments, we get this. So is this fine? Okay, so if this is fine, let's look at how to construct a formula which adds a number of satisfying assignments. So define as follows. So it's we'll introduce an so okay. So in the previous case, we used two sets of variables, x1 to xn, y1 to ym. Now we'll just use one set of variables, the z variables, but we'll introduce a new variable. Uh, so z0. So it's z0. So the formula will look like this. It's z0 and okay, I lost connection again. Yes, I lost connection again. Can you hear me? Yeah.
Yes.
Okay. Yeah. So the formula is going to look like this: phi of Z1 to Zn, or Z0 complement and Zn plus 1 to, sorry, Zm plus 1, because M is smaller than M. Yeah, so this is the construction. And the claim is that the number of satisfying assignments is going to be, okay, so, and the reason is the following. So first of all, notice that okay, so suppose Z1, Z0 to Zm, sorry, Z0 to Zm for a satisfying assignment of 5 plus 5. Then, since Z0 can only be one of the two, 0 or 1, Z0 to Zn can satisfy either this or this,
Your
but
voice is
not.
breaking.
Oh, okay. Okay, so let me start again. So, so let us suppose that Z0 to Zn is a satisfying assignment of 5 plus 5. Then, since Z0 can be either 1 or 0, uh, Z0 to Zn can satisfy this or this, but not both, right? So if Z0 is 0, sorry, if Z0 is 1, then Z1 to Zn must be a satisfying assignment of 5. And if Z0 is 0, then Z1 to Zm must be a satisfying assignment of psi, and all the remaining variables should be 1. So to construct a satisfying assignment for phi plus psi, we, we can do the following. Pick a satisfying assignment of phi and make Z0 1. So that gives us this. Or pick a satisfying assignment of psi, make Z0 0 and make all of these 1. In which case, and that gives us this. So the total number is the addition of the two. Is this fine? Okay, so if this is fine, then let's just see how using these two constructions we can get these three formulas. So for A, it's R square plus S. So we'll first take phi. This gives us R square plus uh, psi times psi times psi. So this gives us R square, and this gives us cube. Yeah, so we can construct something, a Boolean formula with R square plus S cube satisfying assignments. For B, it's R plus S the whole square plus 2S square. So this is R plus S. So this gives us, so this is R plus S satisfying assignments. This has the same. So this whole thing has R plus S squared satisfying assignments. And then it's plus 2S cube, 2S square. So it's psi times psi. This is S square, and we have to make it 2S square. So again, psi times psi. Yeah, so this is S square satisfying assignments. This is S square satisfying assignments. So the whole thing has 2S square satisfying assignments. So we can also construct a Boolean formula with these many satisfying assignments. And what about R square, S square plus 100R? It's similar, but this time I won't write the entire thing. So it's R square plus S, R square S square. So it's 5 times 5 times psi times psi because this is R square. Then what about 100 R? So for that, all we need to do is R is 5. 5 plus 5 plus 100 times. And this gives us 100. Yeah, so we can also construct a Boolean formula with R square S square plus 100 R satisfying assignments. The only thing that we don't know how to do is how to subtract the number of assignments. So even in option D, we can construct a formula with R cube S satisfying assignments and R S square satisfying assignments, but we don't know how to subtract the number of satisfying assignments. So the answer is D. Okay, so this is fine. Let's look at the next problem. So in the next problem, we are given a graph and some of the edges in the graph have weights and all the unmarked edges, that is these two edges, have weight 1. And the question is, what is the sum of the weighted cycle covers of this graph? So again, this needs to be worked out, so I won't ask you what the answer is, but let's work this out. So, okay, so let's first of all, let's just count all the cycle covers over here. So starting from X, we have only one possibility, taking this edge, right? So, yeah, so the first cycle cover would be going from X to Y. Now from Y, we have two possibilities, go to W or go back to X. So let's first go back to X. So this completes one cycle, but still two vertices are not covered. So we need to cover them. So let's start at Z. You, now we have only one option. We can't go back to X because then the cycles won't be disjoint. So we'll have to go to W and then from W we'll have to come back to Z. So Z, okay, so this is uh, one cycle cover. And now what's the weight of the cycle cover? So the weight of a cycle cover is just the product of all the edges included in the cycle cover. Okay, so the edges included are X to Y, Y to X. Both of these have weight 2, so it's 2 times 2. And the other edges that are included are Z to W and W to Z. So it's 3 times 3, and this is 4 times 9, 36. That is, so we took this edge and then this edge back, but we have an option of taking this edge as well. So, and that would give us one more cycle cover X to Y, Y to W, W to Z, and Z to X. So, yeah, and what is the weight of this cycle cover? It's 2 times 1 times 3 times 1. So, and this is 6. Now, are there any other cycle covers possible? Okay, so out of X, we have only one option, take this edge and go to Y. And once we are at Y, we have only two options, this and this. And we have explored both options. So these are the only two cycle covers possible. And so the total weight is 40. Sorry, 42. Is this fine? Okay, let me connect the charger. Okay, so if this is fine, then let's look at this year's week 10 practice assignment. And so the first problem is which of the following problems are Sharpie hard? And select all the correct options. The options are computing the permanent of an n cross n matrix with 0, 1 entries, computing the permanent of an n cross n matrix with entries from -1, 0, 1, computing the permanent of an n cross n matrix with entries from 0 to m for some positive integer m greater than 1, and computing the permanent of an n cross n matrix, all whose all entries are equal to m for some positive m greater than equals to 1. So, which of these are Sharpie hard? Of this,
A,
yeah,
A, B.
okay, A, B, and okay, so A and B are true, but so is C. Okay, so
Oh, C.
it, yeah, so in class you saw A and B, and the reason that C is also true is the following. So any 0, 1 matrix is also a matrix whose entries are from 0 to m, right? So if you could compute the permanent of an n cross n matrix whose entries are from 0 to, yes, uh, I lost connection again. Can you hear me now?
Yes.
Okay, yeah. Okay, yeah. So any matrix in 0, 1, whose entries are in 0, 1 is also a matrix whose entries are in 0 to m. And so if you could compute the permanent of an n cross n matrix whose entries are from 0 to n, you could also compute the permanent of an n cross n matrix whose entries are from 0 to 1, right? So if this is hard, then this also has to be hard. And why is D not hard? So D is not true because of the following reason. So in D, our matrix is just this, right? So all the entries are M. And now permanent of A. So now no matter which sigma we pick, so now no matter which sigma we pick, each and every AI sigma is M, right? So this is uh, M to the N because each of these is M and there are N many quantities. So that their product would be M to the N. And this sum is, so there are N factorial many permutations. So this is M to the N times N factorial. So computing the permanent of a matrix, all whose entries are M, is very simple. All you have to do is just compute M to the N and N factorial and multiply them. And these can be done in polynomial time. So we in fact have a polynomial time algorithm for computing the permanent of an n cross n matrix whose entries are equal to M. And so this cannot be Sharpie hard unless FP equals Sharpie. Okay, so is this fine?
Okay.
Yeah. So the next problem is, oh, so if all the entries of the matrix are greater than zero, but they are not equal, then again it's that would again be hard. So it doesn't follow from what we have seen in the class, but yeah, you can still show that that's still hard. So is this fine? Okay, yeah. Okay, so let's look at the next problem. The next problem is consider an n cross n matrix that has entries from 0, 1. What is the smallest number of non-zero entries of what is the smallest number of non-zero entries that A can have such that permanent of A is not equals to 0? The options are 1, n minus 1, n, 2n, n times n minus 1, and n squared. So which of these is correct?
N.
Yeah. And the reason is this. So okay, what we'll do is first we'll show that there exists a matrix with n non-zero entries whose permanent is non-zero. And then we'll prove that no matter which matrix you pick with n minus 1 non or fewer non-zero entries, its permanent is going to be 0. So uh, let In be the n cross n identity matrix. The number of non-zero entries in In is n, and its permanent is 1 because the only permutation sigma, so that product ai sigma is going to be non-zero is the identity permutation because there are no other non-zero entries. So there exists an n cross n matrix whose permanent with n non-zero entries whose permanent is non-zero. And now suppose that is then but okay, so now let's consider this product for any sigma. Okay, so there are n entries over here. But since A has at the most n minus 1 non-zero entries, at least one of these must be 0 for every sigma, right? So since so okay, let me call this G to avoid confusion with this I over here. As a product, I in M AI sigma I is 0 because at least one of them is 0. And since this is true for any arbitrary permutation sigma, the permanent is 0. Yeah. Yeah. So no matrix with at most n minus 1 non-zero entries can have a non-zero permanent, and so the answer is n. Yes. Now let's look at the next problem. So the next problem is consider the graph in the below figure. All the unmarked edges have weight 1. So this edge, and this edge have weight 1. And the question is in the sum of weighted cycle covers of this graph is what? So let's work this out. Okay, so starting since starting from x, we have two possibilities. We can go to y or go to z. So let's go to y first. So from y, we then have just one possibility going to z, and then from z, we have just one possibility going to x. So one cycle cover is, and what's the weight of this? So this edge has weight 1, this has 2, this has 2. So the weight is 1 times 2 times 2, 4. And another possibility that we had was going from x to z, right? Then from z, we can't go back to x because then y would be left out. So if we go from x to z, we have to go from z to y. But then we are stuck because there is no way to go back to x, and we can't take this edge because then, yeah, then our cycle cover would be this, which we already have, right? Sorry, which won't be a cycle cover because, yeah, it's not disjoint. So the only possible cycle cover is the one that we saw. And so the answer is 4. Is this fine? So let's look at the next problem. So the next problem is let parity x phi x denote the parity of the number of satisfying assignments x of phi. That is, parity x phi x is true if phi x has an odd number of satisfying assignments and false if it has an even number of satisfying assignments. And given formulas phi and psi, which of the following is or are true? Select all that apply. Option A is there is a Boolean formula gamma such that parity z gamma z equals to parity x phi x or parity y psi y. There is a formula gamma such that parity z gamma z equals to parity x phi x and parity y psi y. There is a Boolean formula gamma such that parity z gamma z is not of parity x phi x. And there is a Boolean formula gamma such that parity z phi z, sorry, gamma z is equal to parity x phi x XOR parity y phi psi y. So which of these are true? Okay, so all four are true. So did you see these three constructions in class, or should I like give these constructions? Like, have you seen these three in class, or should I give them?
It was told in class, I think.
Okay, yeah. So I can so I can skip these three constructions. I'll, yeah, so then I'll just show this construction. Okay, so okay, so now let's see how to construct parity Z such that
But will we get these type of difficult questions for exam also?
I so I'm not sure because I have never appeared for this course on NPTEL.
Okay, okay.
Yeah, but mostly I think in exams questions are generally easier than assignment questions because for assignments you have an unlimited amount of time to solve them, right? But in exams you have to solve it in like 3 hours, I guess. So I think the question would be easier.
It is 3 hours.
Yeah. So I think since the time is limited, the questions should be easier.
Okay.
Yeah. Uh, okay, so this is what we want to prove. And when is this true? So this is okay. So first, so these two are Boolean formulas, and we have an XOR between them. So let me first simplify this XOR. So this would be the same as, so okay, XOR of A and B is true. If at most one of A and B is true, right? So A is true and uh, B is false, or A is false and B is true. Okay, so this is just the simplification of XOR. Now let's see how to construct these two formulas separately and then we'll combine them. So first we want to construct a formula which is equivalent to not parity y shy y, right? But that we already know how to do from option C. So this we can construct and then we want to construct a formula which is end of these two. So for this we can use the construction B. So by using construction C and B, we can get this formula. Okay, so let me write it. Use C, and for this use, and let's say that this is parity. Okay, let me call this gamma 1. Okay, so here Z1 is going to be a subset of Z, and it would contain X, Y, and some additional variables. So using C and B together, we can get a formula equivalent to this. Similarly, using C, we can get this formula. Using B, we can get, and then using B, we can combine these two, right? So use C, and suppose we get parity Z2 Let me call this gamma 2 Z2, Z2. Again, Z2 is going to be a subset of Z and it would contain X, Y, and some additional variables. And finally, we want all of these two, right? And that, okay, to construct an OR of these two, we can just use uh, construction in option A. So use A. Yeah, so by using these three constructions, we can construct a formula uh, which has this property. In fact, using these two constructions, okay, so in using these three constructions, we can construct a formula such that even if you replace this XOR with any other Boolean operation, you would still be fine. The reason is that AND, OR, and NOT are a universal set of gates, right? So using just these three constructions, we can construct formulas for any Boolean operator over here. Right? So for instance, XNOR, NAND, NOR, anything. Is this fine? Yes, if this is fine, then let's look at this year's week 9 assignment. So this time we have enough time. Yeah, it's like we have like 50 minutes. So let's just go over all of them. So the first problem is which of the following is or are known to be Sharpie complete problems? Select all that are correct. The options are counting the number of satisfying assignments of in a three-set formula, computing the permanent of 0, 1 matrix, computing the number of perfect matches in a given bipartite graph, and the problem of determining the number of ST paths in a directed acyclic graph. So which of these are Sharpie complete? Okay, so the answers are A, B, and C. And A is easy to see because this is NP hard. Okay, so okay, three set is NP complete, and so its counting version is going to be Sharpie complete. For computing the permanent of a 0, 1 matrix, this we saw in class. And similarly, for bipartite, for computing the number of perfect matches in bipartite graph, I think you should also have seen this in class. So yeah, the options are A, B, and C. And we don't know if D is Sharpie complete or yeah, so it's just A, B, and C. Okay, so now let's look at second problem. So in the second problem, we have which of the following problems have a deterministic polynomial time algorithm? Mark all correct options. The options are sharp span trees, output the number of distinct spanning trees in a given graph, sharp half clique for a given graph on n vertices, output the number of distinct cliques on n over 2 vertices. Uh, Option C is sharp three color, outputs the number of distinct three colorings in a given graph, and option D is sharp two path GUV, which given a graph G and two vertices U and V, outputs the number of distinct paths between U and V of length exactly 2. So for which of these do we know like polytime algorithms? Okay, so we know,
A,
yeah,
A,
yeah, A is true, uh, but D is also true. Yeah, A and D both are true. So A you would have seen in class. D is true because how many, uh, so suppose you wanted to count the number of length 2 paths from U to V, then any length 2 paths from U to V looks like U, W, V. W is any arbitrary vertex, right? So all you have to do is go over all the vertices in the graph, all the vertices W in the graph, which are other than U and V, and check if U to V, sorry, U to W and W to V are edges in the graph, right? If they are, add to your count. So counting the number of distinct paths between U and V of length exactly 2 is very easy. It can be done in like what? Order n cube time, or even order n square time, if you are given the graph as an adjacency matrix. So A and D are true. What about B and C? So okay, so suppose we had polytime algorithms for B and C, then what would happen? Okay, so let's just focus on C, and that would also be true for B. So both sharp three color and half clique. So sorry, both three color and half clique are NP complete problems. So suppose you had a deterministic polynomial time algorithm to compute the number of distinct three colorings or the number of distinct cliques of length n over 2, right? Size n over 2. Then all you had to do to decide whether the graph is recolorable or not, or has half clique or not, is to simply count the number of cliques or colorings and check if this number is greater than 1 or not. If it's greater than or equals to 1, then the graph is recolorable or has half clique, and if it's 0, then it does not have three coloring or a half clique. So if you could count the number of three colors or half cliques, then you could also solve the corresponding decision version, and so NP would be equals to P. So unless P equals to NP, uh, B and C cannot have polytime algorithms. Yeah. And since we don't know if P equals to NP or not, right now we can't say anything about P and C. So is this fine? So then let's look at the next problem. So the next problem is, consider the following statements. Statement P, all promise problems are languages. Statement Q, all languages are promise problems. So which of the following is correct? Only P, only Q, both P and Q, and neither P nor Q. So which of these is correct?
B. Only Q is correct.
Oh, so yeah, so all languages are promise problems. That is true. Okay, so in the chat one, you also wrote A is true. So why do you think A is true? Okay, so yeah, A is not true, and the reason is this. So for any promise problem, so you have three sets pi s, which is a subset of 0, comma 1 star. So these are the yes instances. Actually, I should have this. Uh, the no instances such that pi s and pi no are disjoint. And you also have don't care instances, which are neither yes instances nor no instances, right? For a language, you have yes instances. Okay, so you have yes instances that we call them LES. You have no instances. So this is empty, and there is one more condition. So being a language is a strictly stronger condition than being a promise problem. So you can have a promise problem in which the union of these two is not 0, comma 1 star. So that promise problem would not be a language. However, pick any language. Since yes intersection L no is going to be empty, the language is going to be a promise problem. All you have to do is make these two equal, and don't care if these are empty. So every language is a promise problem, but every promise problem need not be a language. So just Q is correct. Is this fine? Okay, so if this is fine, then yeah. Okay, so if this is fine, then let's look at the next problem. So the next problem is, suppose there is a polynomial time algorithm for unique SAT, then which of the following is or are true? Select all that are correct. P equals RP, BPP equals NP, RP equals NP, and ZPP equals NP. So which of these would be correct?
C.
Yes, C is correct. And the reason is this. So we saw in class that there is a randomized reduction. Let me specify for. So n over here is the number of variables in phi. Okay. So this we saw in class. So now suppose we had a polynomial time algorithm for unique SAT, right? Then here's how we can construct an algorithm for SAT. Take a Boolean formula phi, compute f of phi. Then using the uh, algorithm for unique SAT, decide if f of phi is in unique set or not. If it is, say that phi is satisfiable. If it is not, say phi is not satisfiable. Okay. So the success probability of this algorithm. Okay. So when phi is satisfiable, the success the success probability of the algorithm would be at least 1 over 8n. And when phi is not satisfiable, its success probability is 1, right? So this algorithm can give you false negatives, but it can't give you false positives, right? So yeah, and so this proves that, so this gives us an RP algorithm for 3 sat, and since 3 sat is NP complete, this means RP equals NP. So is this fine? Yes, if this is fine, let's look at the next problem. So the next problem is uh, let phi equals x1 or x2 complement or x3 and x1 complement or x4 or x5 complement be a Boolean formula. If phi is given as input to an unique set decider, then the decider will accept, reject, or either accept or reject. Both are acceptable. So again, this depends on how many assignment phi has. So let me first compute the number of satisfying assignments of phi and then ask you which of these is correct. So phi is satisfied. Uh, x1 equals 1 and x4 equals 1, right? And other variables can take any values. So sharp phi is strictly greater than 1. Sorry, sharp or sharp phi. Okay, so now that we know that sharp phi is strictly greater than 1, which of the options are correct? Okay, so what is an algorithm for unique set? Yeah, the correct answer is C. So what is an algorithm for unique set going to do? It's going, okay, so it's going to accept the yes instances of unique set and it's going to reject the no instances of unique set, right? And for don't can instances, it can do anything. So let pi be unique set, then uh, pi yes uh, is the set of all formulas. Okay, let me use sharp phi is already there over here. Sharp psi equals 1 and pi no is psi such that sharp psi equals 0. And everything else is don't care, right? So let me also write pi don't care. It is psi such that the number of satisfying assignments is strictly greater than 1. Okay, and so our formula phi falls in this set, right? And since any polynomial time algorithm or any algorithm for unique set, all it has to do is accept everything over here, reject everything over here, and do whatever it wants over here. For it can either accept phi or reject phi. Both are perfectly fine. Yeah, so the correct option is C. Is this okay? Yeah. Then let's look at the next problem. So the next problem is suppose F is a family of subsets of x equals to x1 up to x200, and suppose we assign weights W uniformly at random to the elements of X from the set 1 to up to 1000. Weight of a set F subset of F is defined to be the sum of weights of elements in F. According to the isolation lemma, what is the lower bound on the probability that there is a unique minimum uh, weight set in the family F? Okay, so I won't ask you what the answer is because this needs to be worked out. So first, let's recall the isolation lemma. The isolation lemma says this. So by UAR, I mean uniformly at random. So this is greater than equals to. Okay, so this is what the isolation lemma says. And the setting of the isolation lemma is exactly similar to the setting over here that we have. For us, n is 200 and f is so m is 2000 is 1000, right? So from the isolation lemma, yeah, so with probability at least 0.8, you are going to get a unique minimum weight per set in family F. Is this fine? Okay, so if this is okay, let's look at the next problem. So the next problem is, which of the following classes capture the complexity of counting Sharpie, NP, ZPP, or BP? So which of these is this true? Yeah, it's A. Yeah, so this was the simplest question in today's entire session. So let's look at the next problem. The next problem is, cycle is the following problem. Given a directed graph G, decide whether there exists a simple cycle in G. A sharp cycle is the problem of computing the number of simple cycles in G. Consider the following statements. Statement P. There is a deterministic polynomial time algorithm for cycle. Statement Q. There is a deterministic polynomial time algorithm for sharp cycle. Which of these are correct? Both P and Q. Only P. Only Q. And neither P nor Q. So which of these options is correct? Yeah, it's B. So we can, sorry, we can check if there is cycle or not using BFS or DFS in Polytech. On the other hand, sharp cycle is sharply complete. So a polytime algorithm would imply which in turn would imply P equals N. Yeah, and since as of now we don't know whether P equals NP or P not equals NP, right now we do not have a polytime algorithm for sharp cycle, and we also believe that we do. There is no such algorithm. So is this fine? Okay, so then let's look at the next problem. The next problem is consider a bipartite graph G U V E where both U and V have size n. And what is the smallest number n for which any graph G on M edges has a perfect matching? The options are n, 2n, n square minus n plus 1, and n square. So which of these is correct? Or what would you guess? Okay, so the answer is uh, C. Oh, so the answer cannot be n because I can easily construct a graph with n edges which has no perfect matching, right? So A is not true because all I can do is have this graph. U1 up to UN, P1 up to Pn, and construct edges like this. So there is an edge between U1 and V1. There is an edge between U1 and V2. And there is an edge between U1 and Vn. And these are the only edges. So the graph has n edges, but it does not have any perfect matching, right? So there are graphs with n edges which have no perfect matching. You can also similarly show that B is false by just adding these edges. The graph will have two n edges but no perfect matching. Okay, so now, okay, so before I prove that C is correct, let me show you one more thing that there are graphs with n square minus n edges which have no perfect matching. So, okay, so it's mostly similar to this. Let me just copy this. Uh, yeah, so now it's going to have all these edges as well. Okay, let me call this. Okay, so the graph is this. Now, how many edges does it have? So there are n edges going out of U1. So number of edges is n out of U1, or rather, let me say n incident on U1 plus n incident on U2 plus up to n incident on UN minus 1. Okay, so these are the only edges. And this number is n times n minus 1, which is n square minus n. And this graph has no perfect matching because there is nothing to match with UN, right? So there exists a graph with n square minus n edges, but no perfect matching. So the minimum possible number is n square minus n plus 1. But we need to show that every graph with n square minus n plus 1 edges will have a perfect matching. Okay, so now let's show that. So the claim is, what was the number? I think it would be claim tax claim 3. Yeah, so we'll prove this claim, and the proof is by induction on n. The base case is 1. Okay. So when n equals to 1, n square minus n plus 1 is 1 minus 1 plus 1, which is 1. So the only possible graph is this. It clearly has a perfect matching, right? Yeah, so for the base case is true. So now we can move to the induction hypothesis. The induction hypothesis is let the claim be true. Some n strictly greater than greater than equals to 1. And we want to prove the claim for okay, let me try this. Yeah. Okay, so now our graph has n plus 1 vertices and so now size of u, and size of E is going to be n plus 1 squared minus n plus 1 minus plus 1. And okay, let me not simplify this just yet. Okay, and we have perfect matching. So what we'll do is the following. We'll iterative will sort of show how to construct this perfect matching inductively. Okay. So we'll let A and oh sorry, number of edges is at least this. Yeah, because yeah, the claim has at least. So let A in UV be the vertex with the minimum number of edges incident on it. Okay, now since it has the minimum number of edges incident on it, it makes sense to, if you want to consider perfect matching, it makes sense to match this vertex first, because if you were to start with some other vertex, it is possible that by the time you reach to this vertex, you would have exhausted all of its neighbors, right? So it makes sense to start with a vertex with a minimum number of edges incident on it. Okay, and without loss of generality, let's assume that A is in U, say it's U1, UI. Okay, so let Vj be any UI. So we'll add uh, the edge ui comma vj to the matrix. And we want to extend this matching to a perfect matching. Okay. So now ui and vj have already been matched. So what we are going to do is we are going to remove ui and vj from the graph. So if that graph has a perfect matching, just adding ui comma vj to that perfect matching would give us a perfect matching for this graph. So at least are you convinced about this argument that if the residual graph, the one obtained by after removing ui and vj has a perfect matching, then our complete graph would have a perfect matching. Okay, so if you're fine with this claim, then uh, we then let's proceed. So we have added ui vj from the matching. Let G prime be the graph obtained from G. I remove and all edges incident on them. Okay, say G prime is U prime, P prime, and E prime. Okay, so then size of U prime. What I'm going to claim is this. Uh, okay, so let me move this here. So if the degree of U, so if the degree of UI, that is the number of edges going out of UI, were already n, then UI was the vertex with the minimum number of edges going out of it, right? So if the vertex with the minimum number of edges going out of it itself has n, um, if itself has n uh, edges, then then every vertex in the graph has n edges going out of it, and so the graph is a complete graph. Then for oh, sorry, n plus one, yeah, because these are n plus one many, yeah, there. So these are graph on n plus one many, which is right. So yeah, so if the number of edges going out of UI were n plus one, we won't there would be nothing to prove. So let's assume that its degree is at less than n plus one. To remove uh, edges incident on UI plus, okay, number of edges incident on UI plus number of edges incident on VJ minus the number of edges incident on both, because that we would have removed over here as well as here. Okay, so now uh, from here, this is at most n. This can be at most n plus 1, and there is one edge which goes from UI to VJ, which we have already added to the matching. So this is 1. So we are removing two n edges. Okay, so the cardinality of E prime is cardinality of E minus 2n. Cardinality of E is this. Okay, and this is So this becomes n square minus, okay, so these two cancel out. So we have n square plus 1 minus n minus 1 plus 1. So these two also cancel out. So we are left with these many edges, but uh, in our induction hypothesis, we had assumed that the claim was true for n. And the what does the claim say? That the claim says that if an n vertex graph has at least n square minus n plus 1 edges, then it has a perfect matching, right? So from the induction hypothesis, G prime has a perfect graph. And then M union, yeah. So just adding ui comma vj to M would give us a perfect matching in G. So any graph with n square minus any bipartite graph where both the left and right vertices have exactly n vertices, it has to have a perfect matching. So we just have 3 minutes left. Yeah, we can solve this problem. Let's look at this. The problem is, consider the following statements. If P equals NP, then all sharp P complete problems have a polynomial time algorithm. And option P, and the second statement is, if there exists a polynomial time algorithm for sharp P complete problem, then P equals NP. And which of these are correct? Both, only yes, only T, and both are known to be false. Yeah, so only T is known to be correct. Why? Because like, okay, so if T were correct, then you would have so you have a polynomial algorithm for a sharp P complete problem. Now sharp SAT is in sharp P. So you have, all you have to do to decide whether a Boolean formula phi is satisfiable or not is give phi to this algorithm, see if it outputs something greater than equals to 1. If it does, accept. If it does not, that is if it outputs 0, then reject. Yeah, so C is correct. And so far, we do not know anything about A. So we do not know that if P equals NP, then sharp P equals FP. So what we do know is this. P is equivalent to FP equals sharp P, which we know implies P equals NP. Statement S is equivalent to P equals NP. But we do not know as of now if this implies that sharp P equals F. Okay, so we are out of time. So let's stop for today unless you have any questions.
I had a question
Yeah,
regarding NP hard and NP intermediate problems. Are they
okay.
related somehow?
Related in what sense?
Like NP intermediate problems are somewhat easier than NP complete and tougher than P,
Yes.
and NP hard only fulfills part of the condition for NP completeness.
Okay.
So I think they both sit somewhere between P and NP if a gap such exists.
Oh no, okay, no, no, no. So this is P, then this would be NP, Let it- Yeah, fine. Let it be tilted. Okay, I don't have enough space. Okay, so if this is P, then this is NP over, uh, and here you will have, okay, so between P and NP, you would have NPI, and okay, how do I draw? Okay, this whole thing is NP, and NP complete is the intersection of NP and NP hard. Yeah, so if P not equals NP, NP hard won't lie between NP complete and NP intermediate. They contain NP complete.
So, like NP hard is harder than NP complete itself.
Okay, so there exist NP hard problems which are harder than NP complete, but not all NP hard problems are harder than NP complete.
Okay, so do we have any such examples of problems which are NP hard but not NP complete?
Halt.
Other than that, like halt is one I have heard, and I haven't seen any other example.
Okay, so any problem,
Like, can I characterize the problem as that like any problem in NP is reducible to it, but we cannot verify its solution in polynomial time.
right?
So,
Yeah.
like, what would be such a problem that we cannot verify its solution in polynomial time?
Okay, so if you, okay, so first of all, let's assume that the polynomial hierarchy does not collapse. Okay, then any problem in the hierarchy above NP would be such a problem, right? Let's say a sigma 2 problem. So this sigma 2 sat would be an example of an NP hard problem, which is not NP complete unless the polynomial hierarchy collapses.
Okay, so like in the current scenario, I'd assume NP hard to be a superset of NP or something like that, which like intersects with NP complete problems.
Yeah, so it's a strict superset because it contains halt.
Okay, strict superset. Right.
Yeah, so it's strict superset of NP complete.
Okay.
Yeah.
But it may not contain the entire NP class.
Okay, yeah, so that's what Lardner's theorem says, right? So if P not equals NP, then NPI is not empty. So this part is not empty, right? And so this part cannot be an NP hard.
Your
Yeah.
audio got stuck. I
Oh
couldn't
yeah. So okay.
hear.
So Lardner's theorem says that if P not equals NP, then this part NP intermediate is not empty, right?
Yes, yes.
So there exists an NP problem which is not NP complete. Therefore, there exists an NP problem which is not NP hard. So yeah,
Okay.
NP hard is not going to contain all of NP unless P equals NP.
Okay.
Yeah.
Okay. And just one more thing, since this week we have a subjective problem,
Okay.
and it is NP complete or not. So
Yeah.
how do we go about like giving formal arguments for it? Like intuitively we can say and we can show it, but how I make sure that since I'm writing the answers in my own word,
Okay.
the arguments are formal.
Okay. So like did Sir cover any reduction, let's say to vertex cover or vertex cover or independent set? So from three set to vertex cover or independent set in one of the previous lectures?
Okay. No, like this week we have to show that whether three set balanced is NP complete or not.
Yeah. So what I'm asking is in let's say the second or the third week, Sir must have shown this the following in class, right? That three set reduces to independent set or three set reduces to vertex cover, right?
Yeah, three set has been reduced to many problems in lectures.
Yeah. So like you can try to like follow that format. So that format would include the following three things. First, you come up with a reduction algorithm and show that it is polytime, and then show that x is in L implies f of x is in L prime, and f of x is in L prime implies x is in L. So you
Okay,
need
so
to do these
apart
three
from
things.
the algorithm, I need to show that like if x is in L, then f of x is in like L prime, and
Right.
same holds for the complement also.
The converse.
Yeah. So
Yeah.
this part is also necessary apart from showing an
Yeah. All
algorithm.
these three are necessary.
Okay.
Yeah.
Thank you.
Okay. So if there are no other questions, let's end the session today and meet next time. Bye.
Okay. Thank you. Bye.
Bye.
Thank you.